Hi, my name is Eli, and today I will be taking you through a three-part series on speed development in team sport athletes, specifically looking at acceleration, max velocity, and agility/change of direction. In each video, we'll break down the concept and discuss the theory behind it, the technical model, appropriate cues, progressions, adjustments, and training programs to develop it. The first of the concepts we'll be discussing is acceleration. The term acceleration means an increase in speed from either a stopped, motionless position or from a slower moving speed to a faster one. It is a change in velocity per unit of time, and therefore to increase acceleration, we will be looking to either increase the change in velocity or decrease the time. Accelerations are common in all sports and range in their distance and speed. While it varies greatly depending on the sport's demands and the training age and abilities of the athlete, acceleration generally occurs in the first 15 to 30 meters of the sprint. As you can see in the graph showing Usain Bolt's speed throughout his run in the 100-meter final in the 2012 London Olympics, such strong track athletes will have longer accelerations in their races, sometimes accelerating for up to 40 to 50 meters. Biomechanics is the study of forces and their effects on living systems. And because forces determine motion, understanding biomechanical principles that affect speed can assist coaches and athletes in developing running speed. Newton's second law, the law of acceleration, can provide insight into the fundamentals of how to increase acceleration. If force is a product of mass and acceleration, and we assume mass to be constant in running, then force and acceleration are proportional to each other. Therefore, to increase acceleration, we will have to look to increase force production. So before we continue further, here are two clips highlighting the importance of acceleration and speed in sports. In this video, you can see Carlin Lyles pick up the ball and rapidly accelerate to top speed to escape defenders and score for his team. In the second video, Connor McDavid similarly accelerates to top speed quicker than anyone else, gliding right past them to score a goal.
Solid defensive play. His line absolutely dominated every shift. Have a look at this one. End to end, goal line to goal line, 40 kilometers an hour. And then the shot. Thank you very much. For the second straight year, the season.
So while these videos are visual proof of the importance of acceleration, plenty of research exists on the topic as well, proving that acceleration is a predictor of performance in different sports and demonstrating that the high occurrence of short sprints in gameplay. So as we talked about a few slides ago, greater force is the key to increasing acceleration. It is important to note, however, that horizontal force is of much greater importance to acceleration than vertical force is, as we are looking for athletes to push and explode forward rather than upwards. Winkleman demonstrates the need for horizontal force in his 2018 study, showing that 80% of the difference in velocity between elite and sub-elite sprinters is due to the superior horizontal force produced by elite sprinters. Mello's study echoes this, showing a high correlation between horizontal force and acceleration speed. While we'll go into training for acceleration later in this video, I'll briefly note that the best way to improve acceleration ability is through a combination of different training types, including plyometric training and resisted sprint training, amongst other methods like sprint and resistance training. So now we'll really dive into the topic of acceleration and break down the mechanics and technical model behind it. While much of this discussion will revolve around the mechanics used by sprinters, it is largely relatable to team sport athletes as well. So there are three main concepts that make up acceleration ability, those being projection, rhythm, and rise. Projection refers to the body's angle relative to the ground and stresses the importance of sprinters projecting their hips forwards away from the start line rather than standing up immediately. With regards to projection, we are looking for athletes to eat up the space in front of them, producing force, covering ground, and obtaining some level of horizontal velocity through the acceleration. Moving on to rhythm, Rhythm quite simply refers to the sprinter's rhythm, that is, the pace or pattern of their movement. We are looking for smooth running, a steady rhythm rather than short, choppy, inconsistent strides. The pace of the strides should increase throughout the acceleration into the max velocity portion, similar to a steam engine train taking off from the station, which as the train gains speed will make a steadily increasing chugging sound. Lastly, rise refers to a steady increase in angle of the entire body. Tying this back to projection and the total body angle from initial push-off, this angle will increase gradually with each step while maintaining a straight line from head to heel. The rate of this rise will be situationally dependent for team sport athletes, as they have much more visual input to be aware of, such as impediments, defenders, etc., than sprinters who do not have these visual input and are accelerating from a 2-point position. Sprint speed is a product of stride length and stride frequency. But during acceleration, there is more focus on stride frequency, as we want sprinters to push forward, but not over lunge. It is important athletes do not try too hard to be quick with their legs, as often this will result in spinning their wheels without moving anywhere, similar to the cartoon of the Roadrunner, legs spinning rapidly, but the rest of him not moving. So now we'll get into the technical model of sprinting, what we're looking for in our athletes as they sprint. The main technical model can be split into 4 parts: posture, the back leg, the front leg, and the arms. For posture, we're looking for a straight line from the athlete's head to heel, as if there was a ruler that was connecting the 2 parts. The athlete should be looking down and their shins parallel to the body, with the front thigh perpendicular. As mentioned in relation to the rise component, we're looking for athletes to slowly increase their posture throughout the acceleration process, eventually reaching an upright position for max velocity. It is important that the head and heel remain in line throughout the rise. However, coaches should avoid the cue "stay low," as this causes athletes to overcompensate, and the rest of their mechanics then get messed up. Moving on to the legs, we're looking for triple extension of the back leg, that is extension at the ankle, knee, and hip, and triple flexion of the front leg, flexion of the ankle, knee, and hip, with a powerful knee drive forwards for the front leg. It is important that the front ankle is dorsiflexed at full knee flexion, so the force production is in the proper direction when it pushes down. For the arms, there should be a big, meaningful arm drive, punching the arms back and forward. There should be flexion at the shoulder and elbow of the front arm, and extension at the shoulder and elbow of the back arm. Proper arm drive is often dismissed when teaching sprinting, yet it is crucial to force generation, and especially important during the acceleration phase, where the angle of the body means the vertical lift generated by arm drive also has a horizontal propulsive component. Continuing to some further components of the technical model, the first step of acceleration should be big, to project the hips forward. However, it is important not to overreach, as stepping too far in front of the hips will increase braking forces and slow the athlete down. The first step should be behind the athlete's center of mass, the second a bit closer to the center of mass, but still a bit behind, and the third nearly directly under the center of mass or hips. A low ankle recovery is also important during acceleration. It's faster for your heel to pass just over your other foot, rather than come all the way up to your butt, which is how to stay horizontal and get your feet on the ground faster, and then push to more explosive angles. If you lift the heel up too quickly, 2 things happen. First, you will start to cycle rather than drive forwards. And second, you will take too much airtime on each step. Keeping the heel close to the track surface enables a lot of power to be put into the track surface in the horizontal direction. The leg motion should be quick at the start, switching rapidly in a piston-like fashion. It is important to lead with the knee, driving the knee forward to project the hips and body forward. This will also help prevent overstriding. While we want quick turnover in the legs, it is important, as previously mentioned, that athletes avoid cyclical action, that is, leg turnover without moving forward. The legs should switch quickly, but still be stepping forward into space. Finally, ground contact times, the ever important aspect of sprint speed, will be longer during acceleration than at max velocity, putting a greater emphasis on force production and strength. So here's a useful image showing a lot of what we just talked about, with a comparison between Christian Coleman one of the world's top sprinters and the world record holder in the 60-meter sprint, and an Indiana running back. As you can see, the Indiana running back leads with the foot instead of the knee, resulting in overstriding and stepping in front of the center of mass, and braking forces slowing him down. Coleman, on the other hand, has great mechanics with proper foot placement and limb alignment. His ankle is stiff, and he has good shin angles. Here's another example of proper sprint mechanics. This video showing world-class sprinters Noah Lyles and Andre DeGrasse accelerating during a 200-meter race. You'll see that their first step will be a powerful lunge forward with proper knee drive. You see triple extension of the back leg, powerful arm drive, eyes looking down, straight line from head to heel, and exploding out, hips projecting forward rather than straight up. As you can see, they slowly rise up rather than standing up immediately. So now we'll touch on some coaching cues that will help coaches communicate to athletes the ideal technique and mechanics we are looking for to maximize speed and acceleration. Coaching cues can be split into external cues, cues that rely on an athlete's relation to objects outside of their body and environment, and internal cues, cues that focus on a body part within the athlete. While internal cues have been more commonly used in the sports field, recent research has demonstrated that external cues can be easier for athletes to grasp and might be more effective to achieving the desired outcomes. It is likely the case that a combination of external and internal cues is optimal to ensuring athletes understand what they must do while sprinting and remember it in future training and performance. Written here are some external cues, as well as a couple of internal cues that will help athletes understand proper mechanics for acceleration. Athletes can be cued to rise slowly like an airplane off a runway, ensuring they rise slowly and maintain a good posture with a line from head to heel. An internal cue for this would be to maintain a neutral spine while rising. Other cues that are useful are to punch the knee forward or lead with the knee, the internal version, ensuring proper hip drive and front knee and hip flexion. Push the ground away from you teaches back leg triple extension and forces production. Cut your body in half teaches quick leg turnover. Snap your shoelaces to the sky teaches front foot dorsiflexion. Trim the grass teaches low ankle recovery. And finally, rev up the grass or track with your foot emphasizes strong rear foot push-off and great force production. There are endless cues that can be used, and each athlete will respond differently to different ones. These are just some examples. It is important to read your athletes and see what they're picking up and use those ones. So we have mainly discussed acceleration as a general concept thus far, looking at sprint technique in general and in sprinters. The acceleration technical model is similar for team sport athletes as it would be for sprinters. It also varies greatly according to the sport. For example, accelerations in basketball are continuous, repeated, very short bursts with rarely any maximal accelerations. Whereas in rugby, there are still many short bursts, but also more maximal accelerations at longer distances. In football, the demands differ greatly between positions, with linemen rarely accelerating beyond 5 to 10 yards, whereas skill position players must accelerate long distances. Football also has an intermittent nature to its accelerations, with breaks in between plays, and also has more maximal accelerations and velocities. This is why it is so important to do a needs analysis before implementing any training program, to ensure the program replicates the specific demands of the sport and position. This graph emphasizes the difference in requirements between sport and position, and is useful to determining what training drills to do for each sport. As seen in the graph, soccer players must accelerate longer distances than basketball players, and thus it would be more appropriate for them to do greater volume, longer, high-intensity training to replicate game demands. This graph can be very useful while developing a training program. So getting into acceleration training now, acceleration should be the first part of a speed development program, naturally, as it is the first part of the sprint. Given the longer ground contact times during the acceleration phase, there is more of a need for greater force, and thus it is more strength-based than at max velocity. Therefore, it is important for athletes to have a solid base of strength to generate this force and overcome the body's inertia to accelerate. In addition to the strength component, power or plyometric training is important to developing neural drive, elasticity in the tendons and muscles, and the stretch shortening cycle, and consequently explosiveness. We are looking to generate high forces in short times, creating a need for explosiveness in athletes. Finally, the best way to improve sprinting is by sprinting itself. Sprint training can be divided into 4 categories: transfer drills, technique drills, sprint variations, and competitions, the final phase. We will discuss this more in the next slide. We must be very careful with volume and rest in programming sprint sessions. Full go accelerations in sprinting are high stress, high demand movements. They require a lot of rest time to allow adequate recovery for the next repetition. If you do not give enough rest time in between reps, you turn the training session into speed endurance rather than pure maximal speed. Real speed is primarily dependent on the efficiency of the neuromuscular system and central nervous system, and to train at the intensities required to develop speed, the rest between subsequent efforts needs to be sufficient enough to ensure that one of the other systems of the human body is not a limiting factor. Sprint speed will not increase with the fatigued central nervous system. In addition, excessive sprinting can lead to injury, given its high-intensity nature. With all this considered, total sprinting volume per session should not exceed 300 meters. There should be 1 minute of rest for every 10 meters run. Distance should not increase more than 10 meters each week, and sprint training should only be done 1 to 3 times per week. It is vital that good form is prioritized before doing any high-intensity or velocity work to both minimize injury risk and training effectiveness. Acceleration sprint training should be focused on during the off-season, when there is more focus on strength and conditioning and less competition demands. And we also must be careful with introducing new stressors in season. Training must be balanced with sport-specific training, as fast players are useless if they don't have any skill, smarts, and there's no organization to their play. This slide shows a chart that explains the recoveries and volumes allowed for each training method and can be useful for coaches. Expanding on the acceleration sprint training, here are a list of transfer, technique, sprint variation, and competition drills. The foot rudiment series should be the warm-up for most sessions, as it prepares the legs' tissues, muscles, and joints for the plyometric and sprint work. Horizontal skips are useful given the horizontal force required in acceleration. Technique drills, such as wall drills and prowler marches, are useful in developing proper acceleration technique, while sprint variations and competitions introduce different demands and starting positions and more full-on, put-together sprints. With regards to progression of exercises, over training weeks, volume, intensity, specificity, and complexity of training can be increased, while the resistance can be decreased, such as moving from band-resisted sprints to free sprints. For example, sets or distance can increase, difficulty of movement can increase, as well as specificity to sport. It is important to begin with simple, low-intensity exercises, and then progress to harder, more complex, more intensive exercises once the technique is hammered down. Exercises will often be progressed from bilateral to unilateral, from single effort to repeat effort, and extensive to intensive. Progressing the exercises is crucially important to continue to develop the athletes, progressively overloading their bodies and systems and increasing acceleration ability. As acceleration occurs at the beginning of sprints, 10 to 50 meter sprints are most useful when training acceleration. The next 2 slides are a sample training program for team sport athletes. The first slide representing a training week earlier on in the training block, and the second slide being a week later on in the meso or macro cycle, with progressions of exercises. This is simply a rough draft of a training program, but can serve as an example of what a workout program would look like. Each day would begin with a ramp warm-up, raise the heart rate, activation, mobilization, and potentiation. After this, we would get into our sprint work, starting with transfer and technique drills and finishing with some free sprints and sprints with different starting positions. After the sprint work, strength work, and then accessory work, which can be tailored further to fit the sport's demands. This can either be done 3 times a week, or, as seen here, the third day could be fully devoted to speed development. Coaches have plenty of freedom when generating training programs and can introduce more sport-specific stimuli with a Friday workout if they'd like. The first workout on Friday uses plyometric training and more technique transfer and sprint variation drills, whereas the second workout focuses more on sprinting to improve sprinting. That is, actually doing sprints. Coaches can schedule a speed training session on Friday and a lifting session on Saturday, but it is important not to do the other way around, as athletes should be fresh for speed development sessions. Again, this is just an example. There are plenty of ways to go about it. In later weeks, the workouts are progressed, with more complex and intensive transfer and technique exercises replacing the earlier ones to continue to introduce demands on the athletes. For example, the horizontal power skips and wall sprinting are replaced by med ball scoop throws and med ball protection for step. In addition, half kneeling sprints or bilateral broad jumps are progressed to unilateral broad jumps and falling or jump back sprints. In addition, the free sprints and many of the other sprints are progressed to be longer distances or more sets. The strength and accessory work can also be progressed using tempo, volume, load, bands or chains for extra resistance, and decreased rest time, which allows to progressively overload the athletes. Overall, it's important to have a well-balanced, well-rounded training program to push the athletes to improve and develop sprint speed and acceleration speed.